Okay, so hopefully the test didn't stress you out too much. What we have today is mostly a review, just kind of extending some stuff that we've hit on a little bit before. We're going to talk some more about these algebraic numbers. And to do that, I want to talk a little bit more about the form of our whole numbers again. So if you recall our place values, remember the first one, of course, is just our ones place, then our tens place, and hundreds, and 1,000s, 10,000s, and so on. By the way, just a little note here. I'm still putting in my commas every three places, but you're going to notice that most textbooks and most publications no longer do that. They just do something like this. They leave an extra space at every third digit instead of putting in a comma. And that is becoming more standard. There are several countries that do not use the commas. They do it this way. And what the commas get used for in several countries might look like that. That may look strange to us. That is equivalent to our decimal point, 9.12. So we're not switching over to not using the decimal point and using the comma instead of the decimal point. We're still going to keep the decimal point, but we are switching over to using just an extra space instead of a comma at three digits, just so you know. Okay, so anyway, we have our place values here, ones, tens, hundreds, thousands, and so on. And if you recall from what we've talked about with our powers, of course, this is 10 to the first power, which is just 10. This is 10 to the second power, which is 100. 10 to the third power, 10 to the fourth power, going on up the line. And of course, the ones can be thought of as 10 to the 0. Anything to the power of 0, of course, is 1. And we're used to abbreviating our numbers, having something like this, 4,723, written as just 4723. But the full form of that number, as we saw, was 4,000s and 700s and so on. Well, a way that we can shorten that using the powers, instead of the word thousands, hundreds, and whatever, would look like this. 4 times 10 to the third, and 7 times 10 to the second, and 2 times 10. We don't need the first on there. And 3. We don't need the 10 to the 0 or the 1s on there because it's just implied. With that in mind, we look back again, and I know we've covered this a little bit before, but we look back again at our numbers, our algebraic numbers, and we'll see something like 3x to the third plus 5x squared plus 9x plus 2. And you can start to see the similarities here. Instead of our place values being powers of 10 like they are in our whole numbers, our place values are powers of x. And we saw that before. Now some of the differences are, of course, the algebraic numbers here can never be abbreviated in short form. We have to always write out the place values or the powers of x with them. The other big difference we explored is the fact that in a whole number or integer, every digit is positive or every digit is negative. But we've seen with our algebraic numbers, we can have each digit positive or negative on its own. So here, the 7x squared, that digit's positive, and the 5 or 5 ones is positive, but the negative 3x is negative. And we've seen that a little bit before too. So some things that we need to, some other similarities that we need to draw between our algebraic numbers and our whole numbers and integers. Our place values in our whole numbers and integers occur in something we call descending order. Descending order just means the largest place value comes first. And what that means, since we're dealing with powers of tens, it's the place value with the largest power of 10 comes first. Obviously, 10 to the third comes before 10 to the second because 3 is bigger than 2. The same is going to happen, as you see with both of these algebraic numbers. The same is going to happen with our algebraic numbers. The largest power of the variable comes first. The digit with the largest power on the variable comes first, and we go down from there, progressively smaller. Also, if I have a number like 4,307, like that, if I were going to write that out in expanded form, I would have my 4 thousands, or 4 times 10 to the third, and my 3 times 10 to the second. Do I need to put the 0 times 10 to the 1 or 0 times 10? No, I can just skip that and then put my plus 7. If I were going to abbreviate it, I have to put that 0 back in there. But if it's written out in long form, there's no reason to put in 0 times 10 or 0 times 10 to the 1. The same thing happens in our algebraic numbers. Since our algebraic numbers are always in long form, there's sometimes missing digits. We might have 5x to the third plus 2x squared plus 7. What digit's missing here? We have x to the third, we have x squared, but we don't have an x to the 1 or an x. So technically what's there, as we've also seen this before, is an x to the 0. We don't have to write it in there when we're just writing the number like this, but often when we go to calculate with it, we have to put it in there to hold that place. Any questions so far? So now our descending order gets to be a little more confusing if we throw a second variable in there. So like here, it's pretty obvious the 5x squared should go first. But what would go next? The 7x or the 9y? You got it. We will put the 7x first because we've started using the x already for our descending order. Oops, go ahead.
Don't you also do alphabetical order with that too?
Well, if you have multiple variables in the same digit or same term, yes, you go alphabetical order. When you're going descending order, it's not necessarily done that way. If there's no other deciding factors, then you can use alphabetical order. But here, the main reason that x would go first is we already used the x to determine our first digit. It has the highest power. So we would use that next. So if this were like 3y to the 5th plus 7x squared minus 2y plus 5x minus 3. Obviously, the 3y to the 5th is the highest power. Now, the 7x squared is a higher power than anything else, but since we started with the y's, we should continue with the y's. So the question becomes, well, what do you do with the 7x squared? A lot of times what we'll do is we'll actually do this, start counting back up with a different variable. For this course, we're not really going to worry about doing anything with more than one variable in it as far as descending order. If I ask you to put something in descending order, it'll pretty much always be just a single variable. Something like this is kind of confusing. Okay, so let's just kind of review doing our operations with these algebraic numbers or polynomials. Actually, let me put just a couple more terms out there. Polynomials. And one of the things we refer to in our polynomials is something called degree. The degree is just that highest power. So this one is in descending order. I've got the largest power of my variable first, and on down to my smallest. What is that largest power? 3. So this would be said to have a degree of 3, or a third degree polynomial. If you get into solving equations, the degree, or solving and graphing, the degree of the equation determines what type of graph it'll make. A first degree equation, of course, is a straight line, and then we'll look at those a little bit in this course towards the end of the summer. A second degree equation forms kind of a U shape, which is called a parabola. We'll just touch on those a little bit. And anything higher than a second degree, of course, second degree would be x squared or y squared or whatever. Anything higher than that, we're not going to deal with in here. That would be something for like a college algebra course or something like that. But that degree, that largest power on the variable, does go a long ways towards determining the shape of the graph of the line. Okay, so let's review our operations here. If I have something like this. That looks kind of ugly, but what I'm going to ask you to do is give you the command of simplify. When I ask you to simplify, what does that mean?
You're going to be adding like terms together if you can.
So we're going to combine anything that we can combine, and we're not necessarily going to get it down to a single number or a single digit. And that is, as I've mentioned before, the biggest thing that people will mess up on these is they try to combine further than they can, further than they should. So remember, we can only combine things that have the same variable. Bless you. So I'm going to start out with that. This one has an x, so I'm just going to circle all the ones that have an x. Now, what if they have an x and a y? Are they still the same? No. It has to have just that variable, the exact same variable. If there's anything extra, it's different. But not only does it have to have the same variable, it must also have the same power.
The same exponent.
Perfect. Yes, the same exponent. Very good. So here we've got 5x squared. Can I combine that with the 7x? No. The 2x? No. Negative 8x squared? Yes. 5x squared and negative 8x squared make?
Negative 3.
Negative 3. Perfect. Negative 3x squared. So I've used those up. Now I got the 7x and the 2x. 9x. Positive 9x, so plus 9x. So I've used those up. So now I have y's and I have the 2. Now the number with no variable usually gets put at the end unless we have some specific form. So we're going to wait and put that at the end. I'm not going to count back up the y's like I showed you. So I'm going to actually start out then with the highest power of y. Is there anything to combine with the negative 3y squared? No.
No.
Is there anything else I can combine here at all? No. So I've got my positive 5y, my positive 2, and that is it. Looking at this one, is there anything I can combine? Okay, this is a tough one. Every single one of them has both an x and a y in it. It's the powers, the exponents, that are different. So as we look at them, we have to identify what they are. This is x squared y. Is this x squared y? No, that's xy squared. Is this x squared y? Well, it's x squared and y squared. So we got to be careful. That one's not the same because there's a squared on the y as well. How about this one? Nope. That's xy squared, not x squared y. And this is just xy. There is nothing that is the same as that one. So there's nothing I can combine with that one. They have the same variables, but they have different powers. How about this one? 3xy squared. Is there anything that's the same as that? Perfect. The negative 5xy squared. So I have 3 and negative 5 make negative 2, and that's just xy squared still. We keep the same name. Now we've got the 7, positive 7, x squared, y squared, and the positive 3xy. Now I didn't necessarily stay strict with descending order here. The 7x squared, y squared probably should have gone first. Just because not only does it have the highest power of the x, but it also has the highest power of the y. And that is something that is used if there's two terms that both have x squareds, both have the same highest power. The one that has the highest power on the second variable would usually go first. But anyway, those are the right digits. I don't think my math lab, unless it specifically asks for descending order, I don't think my math lab is picky about what order you put them in.
So, when you're looking at descending order, it'd be 14, obviously. And then the 7, do you look at the powers first or the actual numbers?
You look at the powers first. Okay. So this is x squared, and this is also x squared, but this is just y, and this one's y squared, so technically that 7x squared y squared should go first. Before the 14. Just because they're both x squareds, and this one has the y squared. And then probably like that. This is actually one where you really, if you wanted to get an exact descending order, you'd have to specify which variable, because both x and y do have a power of 2 in them. And so you'd almost have to specify, I want it in descending order according to x, which is what I have here. This is according to x. Or descending order according to y. Would be slightly different.
So you wouldn't look at according to x and look at the y at all?
Yeah. You only look at the y's if there's like a tiebreaker. Like there's 2x squared, so that's why we looked at the y to put this term first. Same here, both of these have an x, but this is a y squared, so that's why we put that one first. Okay, so in your notes, I want you to see if you can remember how to do this before I review it. Give that a shot in your notes. See if you remember how to make that work. So the first thing we have to do is we're just going to set this up like we would any other addition. 5x squared minus 7x plus 8. And 3x squared plus 9x minus 13. And then we're just going to add down the columns like we would, again, with any other addition. The difference is some of our digits are negative. So we have 8 plus a negative 13. Well, it's positive 8, negative 13. Bless you. That results in negative 5. So we've got a negative 7 plus 9 for our x's. Negative 7, positive 9. That results in positive 2. And, of course, that's still x. And then 5 plus 3 is 8x squared. How many of you had that? Does that look familiar? Okay. The addition wasn't the tough ones. The really tough ones came when we threw in subtraction. Like this. Give that one a shot in your notes. So let's line it up. And now remembering that we are subtracting down each column. So this is a negative 9 minus 2. Now I always write these out so I can change them. This is going to become negative 9 plus a negative 2. So negative 9 and negative 2 make negative 11. 5 minus a negative 7 becomes 5 plus 7, or positive 12x. Perfect. How about 4x squared minus 9x squared? Perfect. Negative 5x squared. Wonderful. Any questions? The difficulty with the subtraction, of course, is with the negatives, keeping track of what really has to be combined there. I never, ever subtract with negatives. I always change it to addition, adding the opposite. I make a lot fewer mistakes that way. Then, of course, we looked at multiplication. I'm going to have to try that one in your notes quick. So you could write this out and multiply it out the long way with 3x minus 9 times 5x to the 7, like that. Or I'm just going to do it the short way and do just distributing. So I have 5x to the 7th times 3x squared. What do I get? Perfect. 15x to the 9th. 5 times 3 is 15. X to the 7th times x squared. We add the powers when we multiply variables with exponents. 7 plus 2 makes 9. 5x to the 7th times negative 9. Negative 45. X to the 7th. Perfect. I want you to try this one then. Oops. I'll change that. Give that one a shot. See what you come up with. Okay, so we'll start out with the parentheses. Anything to do inside this first set of parentheses? No, so we're going to do something to it. We're going to multiply by the 3x to the fourth. Times 5x to the third gives us 15x to the 7. Good. 3x to the fourth times negative 2x is negative 6x to the fifth. Good. Now this set of parentheses, there's nothing to do inside it again. Anything to do to it. Distribute by a negative 7x to the third times 3x to the fourth gives us negative 21x to the seventh. Good. Negative 7x to the third times 5x squared. Negative 35x to the fifth. All done? No, what do we still have to do? We have 2x to the seventh here that we have to combine. So it's a 15 and a negative 21 make? Perfect. Negative 6x to the seventh. Then these are both x to the fifth, so we can combine them. Negative 6 and negative 35 make? Careful. Negative 6 and a negative 35. So negative 6 and negative 35 is a negative 40. Perfect. This is a negative, but it's not subtracting a negative. Yep. Yeah, I used the negative twice. Yep. Yeah, you can either think of that as a negative 6 minus 35 or a negative 6 plus a negative 35. We might look at something like this. Now we haven't really done anything like this in the homework yet, so I'm going to go through this example with you. We would set it up just like we would any other multiplication, with one below the other. And just like any other multiplication, if with whole numbers, we'll start with this last digit of the bottom number, and we multiply. Negative 7 times 5 is negative 35. Negative 7 times 3x is negative 21x. Good. Now we've done everything. We've combined every digit of the top number with the negative 7, so we're going to move over to the 2x. We either leave a blank or a 0 down here, but I'm going to hold off for a second on that. We got 2x times 5 is positive 10x. That has to go here because it has to line up with the other x. Then we've got 2x times 3x is 6x squared. We do the 2 times the 3, but we also multiply the names. X times x is x squared. So we have negative 35 here. We have to combine the negative 21 and the positive 10x makes negative 11x. Negative 21, positive 10. Looks like that. And the 6x squared. Look familiar at all? A little bit? Okay. We also looked at division. We might run into something like this. Meter. So 28x to the fifth y squared minus 42x to the third y to the third plus 35x y to the fourth divided by 7xy squared. Now this is different than simplifying a fraction. We are actually being asked to divide here. So we're going to start out with the numbers. We do it digit by digit. So we start out with the first one. 28 divided by 7 is 4, right? So then what power of x is going to go there? X to the 5th divided by x. Think of this. 5 minus 1 is going to be 4. When you divide, you subtract them. How about the y?
It'll just be y.
Well, actually, the y's actually disappear because it divides out. Y squared divided by y squared is just 1, so we don't need to put it in there. It's not y to the 1, it's just 1. Technically, if you do 2 minus 2 is 0, and y to the 0 is 1, so we don't have to put it in. So the y squareds cancel out. So then we move on to the negative 42, x to the 3rd, y to the 3rd. Divided by 7 gives us negative 6, good. How about x to the 3rd divided by x? X squared, good. 3 minus 1 is 2. And y?
Wouldn't that one just be y then?
Yep, because 3 minus 2 is 1, so it's y to the 1 or just y. Perfect. So then we got 35x y to the 4th divided by 7. Positive 5, good. How about the x? The x cancels out. And y? 4 minus 2 is 2, so squared. So it's just like our division that we did before with, a single digit divided by a single digit. You just got to do it once for each digit. We will look at that again more later too, just so you know. Our last thing for today is we want to look more at word problems and setting up word problems. And we've talked about it before that when you have more than one item you're trying to find, one of them has to reference the other. We looked at rectangles and perimeter of rectangles. Let's say that we are told the length of a rectangle is 3 times the width. The perimeter is 72. Find the length and the width. So what we're dealing with is a rectangle. Since it's visual, I'm going to draw a picture. And we have the length and the width. We know our formula that goes with this is perimeter is 2 times the length plus 2 times the width. And we know that the perimeter is going to be 72. I'm going to put that in there. But we don't know how to solve an equation with 2 variables in it. We got both L and W here. We have to get rid of one of them. To do that, we look into the problem and see if one of those numbers, one of those values references the other. And in this case, what is it? The length is 3 times the width. So L is equal to 3 times W, or 3W. So what that allows us to do is replace the L here in this formula with 3W. So 72 equals, instead of 2L, it's 2 times 3W plus 2W. What do we do next? Well, we must, gotta be careful, we gotta multiply first. 2 times 3W is 6W. Then we can add the 2W. So 72 equals 6W plus 2W is 8W. And then? Yep, divide the 8 into the 72, gives us 9 equals W. Are we all done? No, we do still have to answer a question. W equals 9, but we're also asked to find the length. 3 times W becomes 3 times 9, or 27. Now, me being uptight like I am, I would want to add those up and make sure the perimeter still adds up to 72, and you can double check that. We've done problems like that last week, but I wanted to put it out there so that we could move on to this next type of problem. Pete is 5 years older than Pat. Or, let's not put the same letter there. Here, let's do this. 5 years older than Chris. Tom is 2 years younger than Pete. The sum, what's the word sum mean? Add them up, the result of an addition problem. The sum of their ages, so we're adding up their ages, is 47. Find their ages. So we have 3 here. We have Pete, we have Chris, and we have Tom. And again, we know that they're going to add up. That Pete's age plus Chris's age plus Tom's age has to add up to 47. But we have 3 variables. We have 3 items here. We have to get rid of 2 of them somehow. So we have to look for references. Pete is 5 years older than Chris. What does that tell us?
5 plus K.
Yeah, 5 plus K or K plus 5, either way we want to write it. So obviously we're going to have to leave Chris as K if Pete's going to be K plus 5 or 5 plus K. The difficulty here, though, comes with Tom. Tom is 2 years younger than Pete. So I could do P minus 2. The problem is we're not using P. What variable are we using here? We've decided to use K.
So it would be K plus 3.
Very good. And the long way to get to that, Pete is K plus 5, right? And Tom is 2 years younger than that, so it's Pete minus 2. But Pete is K plus 5, so that does work out to be K plus 3. 5 minus 2 is 3. Does that make sense? No? Okay. If you look at it on a number line, here's Chris, and here's Pete. Pete is whatever K is plus 5, right? Tom is 2 years younger than Pete, so that puts Tom right here. Well, 2 years younger than Pete is still 1. I put way too many lines in there, didn't I? Let's redo that for a second. Sorry. There. So 2 years younger than Pete is still 1, 2, 3 years older than Chris. So it's K plus 3. It's a tough one because we're referencing different things. You got to somehow change them so they're both referencing the same thing. But if Pete is K plus 5, if we got to go back 2 to get to Tom, well, 2 less than that would be K plus 3. So, back to our equation now. We can put in, for Pete, we can put in K plus 5. For Chris, we're going to leave it as K. Tom becomes K plus 3 equals 47. What can I do with that mess? Combine, I have 3 Ks, which is just going to be 3K, plus 8 equals 47, and then Subtract 8. 3k equals 39. And then divide by 3. K equals 13. Am I done? No. Still got to answer the question. The question was find their ages. Chris is 13. Pete is going to be 13. Oops, go ahead.
I was going to say, so we can just add the 5 to the 13.
Yep, 13 plus 5 is 18. Go ahead.
And then minus 18 from 18.
Yep, 18 minus 2 is 16, or we could do, 13 plus 3 is 16. And at this point, I'd want to go back through and make sure those still add up to 47, just to be sure. Let's do one more of those. No? 18, 13, and 16. Let's say Don is 3 years younger than Sam. Paul is 2 years younger than Don. The sum of their ages is 34. Find their ages. So we know the sum of their ages is 34. So Don plus Paul plus Sam is 34. What'd you get for the variables over here when you defined them? What'd you put in for Don? S minus 3. Very good. How about for, so that means Sam is just going to be S. What's Paul? S, yeah, S minus 3 minus 2 or S minus 5. Good. Any questions on where those came from? So over here, Don is S minus 3 plus Paul, oops. Paul is going to be S minus 5, and Sam is just S. Should have picked a different variable than S, because S looks like 5s when I write them. So what do I have here when I combine? 3S what's next? minus 8 equals 34. Okay, then what? Add 8, okay. So 3s equals 42, and then divide by 3. So s equals 14. So which one of them is 14 years old? Sam is 14. Good. How old is Don? 11. Good. S minus 3 becomes 14 minus 3, which is 11. And how about Paul? He's 9. Good. S minus 5 is 14 minus 5, which is 9. Or you could have done 11 minus 2 because he's 2 years younger than Paul. What do you think? Okay, I think you guys have had enough for the day with the test in there. So there is a quiz that is optional. It's extra credit that will close. It would be due at 11:59 p.m. tonight if you choose to take it. What I do with that one is whatever score you get on that one, I use it to replace your lowest other quiz score if that other quiz score is lower. If it's lower than any of your other quiz scores, I pretend it never happened. But I won't do that till the end of the semester. So it's worth it to have there in case you struggle with a quiz later. There is also a new homework assignment that is going to be due on Tuesday. Because I was nice enough to give you Monday off. Not that I have a choice. The buildings will be closed. You guys have a great weekend. Enjoy your 4th of July. As always, the computer labs will be available till noon for you if you want to stick around and get started.